in this problem, we have two parallel plates. By parallel plates, I just mean, hold on, I'm sorry. Pretend like you have two pieces of paper that are actually pieces of metal, all right? And they're parallel to each other, and they're charged. So one of them is charged positively, the other one's charged negatively. They're parallel to each other. And there's just empty space between them. Okay, when you have a situation like this, you have what's called a uniform electric field between the two spaces. So the field between the two spaces does not weaken the further away you get from the positive charge. It stays constant or uniform throughout. That's what these represent. That's the electric field between the two plates. Uniform electric field. I am going to say that that electric field it has a value or a magnitude of 795 newtons per coulomb. Now, if I placed a positive charge anywhere inside of this field, a new positive charge, anywhere inside of this field, you would expect it to experience a force because you know that that positive charge is going to be repelled by the positively charged plate and it's going to be attracted to the negatively charged plate. And in fact, once you know that this charge is going to go in the direction of the field arrows. Why are the field arrows in this direction? Because remember, by definition, field arrows go away from positive and into negative. So if I gave you a problem that did not give you the negative and positive plates, but just said that there was a positive charge placed into that electric field, you could calculate its force and know the direction that it travels. You know that it goes in the direction, positive charges always go in the direction of the field. So if the field's to the right, that positive charge would experience a force to the right. If I placed a negative charge in here, that would experience a force to the left. Because remember, this was a negative plate, that was a positive plate. Negative charge would be attracted to the positive plate, repelled by the negative plate. So positive charges always experience a force in the direction of the field, always, 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 always. And negative charges always experience a force opposite the direction of the field. So in this question, I'm going to say that the charge has a value of 3.2 nanocoulombs, right? And it's going to be positive. So Q, I have to get a new marker, 3.2 nanocoulombs. And all I want to do is calculate the force, the magnitude of the force acting on that charge, and what is the direction. Well, F equals Q times E. Electric force equals the charge times the field. This is analogous to gravitational force, is mass times field G, little g, 9.8. Instead of mass, we're not talking about gravity, we're talking about electricity. So instead of mass, we're talking about charge. Instead of the 9.8, the meters per second squared, the gravitational field, we're talking about the electric field, which is, in this case, 795 newtons per coulomb. It's a very easy question. So we're going to put 3.2 times 10 to the negative 9, then multiply that, because we have to be in coulombs, not nanocoulombs, times 795. And that comes out to be, it's 2.54 times 10 to the negative 6. So we'll just round it to 2.5 times 10 to the negative 6 newtons, and it would be to the right, in the same direction as the field, because it's a positive force.